Okay, so I know you're kind of sick of this example, but I'm just going to beat it to death real quick. So the theorem we just proved was the following. The product of two integers is even if and only if at least one of its factors is even. Maybe both, maybe just one, it doesn't matter. You always get an even product. The sum of two integers is even if and only if both summands have the same parity. So in case you forgot, same parity means either both even or both odd. So even plus even is even, odd plus odd is even plus odd is odd. And it's commutative. So we proved this in class, we proved this now on YouTube, and so we know the both of them together. And together they prove pretty much everything you could possibly want to know about even and odd as respect to algebraic operations. And the advantage of these things is it allows us to give more natural proofs of the kind of statements we've already been proving. Because now instead of having to treat even as some like word which just generates a k out of nowhere, like you don't think of it that way. 4 isn't even because it's 2 times 2, it's just even because it's even. 17 is odd. 26 is even. I mean, you don't think about division and calculations to do this. It's just a fact about the numbers. And maybe that's how we should treat it. And these theorems allow us to do that. So let's give an example. So for example, just consider the following sentence. For all n and z, n squared plus n is even. I'll write it with the notation we've been using. So this is saying is no matter what integer you plug into this polynomial, you always get an even number out. And we've actually proven this in class already, but this is going to be an alternate proof, and it looks like this. So proof. Let n and z be arbitrary. Note that that n squared plus n is equal to n times n plus 1. Okay? So already, this is starting to look a little bit like theorem 1. If I knew that one of these guys was even, I could conclude the whole thing is even. Cool. So let's do this. So since n is arbitrary, it's either even or odd. And so we're going to use those two cases. Case n is even, or case n is odd. Okay? So since n is even, and n squared is n times n plus 1, n squared plus n is a product of n, which is even, and n plus 1, so is even by theorem 1. Okay? Which is what we wanted to show. So in this case, we're done. In this case, it's not much harder. If n is odd, then n plus 1 is odd plus odd, so is even by 2. So n squared plus n is odd times even, which is even by theorem 1. And so in both cases, we get what we were looking for. We get that n squared plus n is even. And there's a lot of different ways to see this. And again, we could do this by the definition, but I think it's kind of nicer once we know these theorems, once we've proven these theorems, we've really done it, then we can use them and we can get these sort of results without all the hassle, without all the extra variables. We can just do it. All right, so I hope this was helpful. And we're really done with this kind of problem. Okay.